Yes, I'm going to tell you about dark matter direct detection with noble liquids, with experiments based on noble liquids and primarily designed to search for weakly interacting massive particle as a leading dark matter candidate. And so, just this hypothetical new particle produced in an early phase of this universe, maybe a billionth of a second after the Big Bang. And it has not only received a lot of attention in terms of papers published. This plot is funny because the height of the column is the number of publications. Has received a lot of attention in terms of papers, but also experimentally, the effort has been focused for many years now on WIMPs. For good reason. On the other hand, the absence of a signal so far has led to a renewed interest in alternative dark matter particles, and we should keep our mind open and look everywhere, from fuzzy dark matter. This plot shows some of the candidates to primordial black holes. You see the huge range in masses, and also the difficulty of the interest in the WIMPs is also that it is relatively approachable experimentally. If these particles indeed exist in the halo of this galaxy, they will care, although rarely, to interact with normal matter, and we could detect it in particular in experiments, ultra low background experiments on Earth, or maybe indirectly from the annihilation products in the dense region of the universe, or we could even produce them at accelerators. So the reason for the WIMP, the idea of the WIMP is a very well motivated, and I say especially experimentally, is challenging, but is doable. The challenges of detecting these particles, dark matter candidates, with an experiment on Earth are due essentially to the very low rate of interaction. We can calculate taking the rate of WIMPs in the halo of this galaxy, assuming a cross-section from physics, taking a mass, and we can calculate in the standard scenario of a WIMP scattering off a nucleus of an atom, we can calculate the rate that we expect in a detector. I skipped that slide, but these rates are extremely low, and especially the energy which is imparted to the nucleus or even to the electrons, we will see, are very tiny. So detectors must be quite large, contain a lot of atoms, nuclei, and have a very low energy threshold in order to sense this tiny energy transfer. But essentially, the holy grail of this search is really to have redundant discrimination of the background over the signal, because the background, and especially background due to neutrons, is, of course, the ultimate enemy that we have to fight. And this background has many origins, from cosmic rays to intrinsic radioactivity of all the materials. And, of course, ultimately, we call it background, but we are looking forward to see neutrinos, of course, in this detector, solar neutrino, atmospheric neutrino, supernova neutrino. But the search for WIMPs has made, as I will show in a moment, a huge progress, mostly by this experiment overcoming this huge challenge of reducing this background rate in this detector to extremely low level. So where do we stand today? This plot is approximately a complete picture of the state of the art today. What you have is the scattering cross-section normalized on nucleon here on the left, on the vertical in square centimeter, versus the mass of the WIMP. And so we have gone from the time we started, I mean, actually decades, a couple of decades ago, with event rates which were even more than a few events per kilogram per day. We are searching today for WIMPs, or for particles, which will give you a rate at the level of one event in 1,000 kilograms if you wait for 1 year. So that's the needle in the haystack that we are looking for. That's the next generation experiment that I'm going to tell you a bit about it. And the current limit, the best, we haven't found any sign of these particles, and we have placed the most stringent limit with the xenon 1-ton experiment. As you can see, the black curve, and you have a variety of experiments there. We have also shown that not only in the high mass region, hundreds of GeV, TeV scale, these noble liquids are ideal, but also at the lower mass region, we have made quite some impressive progress by using the ionization signal only. And I think that's on the next slide, where you see just two examples on the left, what dark side 50 has been able to achieve with S2 only. And on the right side, we have the results yesterday were mentioned briefly from xenon 1-ton using S2 only analysis and the mid-Gauss effect. And you can see the impressive sensitivity that we have achieved even in the below the few GeV mass region with these noble liquids. So why, okay, if you look at the world map of where these experiments are located and what targets and what experimental approach they use, you're going to find that the game is being played now mostly by these noble liquids. So why are they so interesting? What makes noble liquid ideal? Wimp targets. And so first and foremost, I mean, for me is the last point, that you have these two signals, excellent ionizers and scintillators, that result from the passage of irradiation through them. And so the availability and the simultaneous detection of ionization and scintillation in noble liquids make them extremely powerful, but they're also dense. You have there both the Z and the atomic number, and the density. So you have a 3 gram per cc for liquefied xenon when you cool it to about minus 100 degrees C, and for argon is about half. So dense liquid, and with a temperature which is, of course, as I said, relatively warm. For xenon and argon is 87 Kelvin. You have a large nucleus in the case of xenon, which is also very attractive for spin-independent coupling of WIMPs, but you also have a large number of isotopes in natural xenon which have spin, which allows us to search also for spin-dependent coupling. And then you have the yield, how many photons per kV, how many electrons per kV, and these are, as I said, xenon is the best ionizer among the noble liquid with about 64 electrons per kV. So the other point is what is written there, the radio purity, no intrinsic radioactivity except for this krypton-85 in xenon and the argon-39 that we have mastered how to reduce and overcome, or to reduce to the level that are required. And of course, I mentioned the spin, the nuclei, the isotopes with spin. And finally, I guess, of course, the challenge is that they are dense, and this allows you to make very massive detector at a relatively modest scale and also modest cost, because even if you take into account the fluctuating price of xenon or even argon when you have to clean it from argon-39, even a few $1,000s per kilogram is a relatively advantageous cost with respect to other target. So this, Giorgio mentioned many times yesterday, monolithic. I think we cannot emphasize more the fact that you have a liquid, you take this gas, you liquefy them, and you put them in a vat, and you have a homogeneous, dense, massive target, a monolithic detector. This is very powerful. Something to remember as well. So the formation of this light and charge in these noble liquids has a very complex interplay between the process of ionization with the recombination which follows, because the electron-ion pairs tend to recombine with each other. We try to separate them by applying a field, but at the same time, oh, that's not me. At the same time, the atoms and the molecules are excited, producing these excimers, which then go to the ground state with the emission of these very deep UV photons, the 175 or so nanometer for xenon, 128 nanometer for argon. And these triplet and singlet states of these excimers are very different, especially in liquid argon, where the separation in time characteristic of the triplet and singlets is used to do pulse shape discrimination effectively in liquid argon, as I'll show you. The challenge is, and then a lot of the energy, once you have a particle, a WIMP or a neutron in this sketch, or a gamma ray from radioactivity, you're going to have these two channels. You have to produce electron free carriers that you keep them free because you minimize the attachment to impurities, you overcome recombination, you have also scintillation photons, and the process of recombination actually leads to the formation, as is shown here, of also excimers. And so you have a component of the scintillation light which comes from recombination. Very, very complex process which in the end give you the two signals, and a lot of the energy goes also into heat, which so far we haven't detected yet. But we take advantage of light and charge, and we detect them simultaneously in the so-called two-phase time projection chamber, which is at the basis of these experiments I'm going to briefly discuss in a moment. And as it was discussed also yesterday by our nice talk on xenon 1 ton by Christian. So you have this container where you have this purified, ultra-pure, ultra-cold liquid xenon or argon, and if you have a particle interaction, you're going to have a certain number of scintillation photons, which is a very prompt few nanosecond signal, and then you have a number of ionization electrons. The ions are left behind because they move 10 to the 4, 10 to the 5 times slower. You don't detect them, and so the electrons are drifted against the applied field. And then we play the trick of the two phases really to have a built-in amplification region. We actually extract the electrons from the liquid to the gas in this tiny gas gap above the region here, and we accelerate these electrons in gas where they actually produce additional luminescence of photons. So we turn the electron signal into a light signal, and therefore both the light, direct light, and the proportional scintillation light, as we say, because proportional to the energy deposit, are detected by the same photosensors, which are placed typically just in the gas above and in the liquid below the cathode. So for the readout of these light signals, S1 and S2, as we call them, we use photomultipliers, which we had to develop, of course, with a lot of effort in the last 15 years with manufacture, because you don't find phototube easily sensitive to 175 nanometer, neither that they stand low temperature, high pressure, and also which have low radioactivity for our ultra low background purpose. And so the monolithic, this sensitive volume that we have, which is active, enclosed by these electrodes, which we call the cathode, and the other electrodes, can be fiducialized, as we say, because what we end up measuring with this two-light signal is both the depth of the interaction through the drift time, and then also we have the X and Y position of every event, which we can infer from the pattern of the light on the top array. So having an X, Y, Z readout or possibility, we have a 3D position sensitive detector, which enables us to fiducialize the central region, typically of the detector where the background is lowest, as a lot of the radioactivity, at least from material, stays on the edges. So the power of fiducialization, and also you have the ratio of these two signals is dependent on the type of particle. Nuclear recoil have usually a larger DEDX, and so you're going to have a quite different ratio for a nuclear recoil of the same energy as an electronic recoil. That's the basis of discrimination. And for liquid argon, in addition, we use pulse shape discrimination as the triplet component for a nuclear recoil in argon is highly suppressed. I will show you maybe later. So that's the principle of the TPC. Xenon 1 ton, which is done by now because we're building Xenon N ton 1. Soon I'll show you a beautiful picture. Was the largest TPC with liquid xenon or of any noble liquid built so far as I know. 3.2 ton of xenon needed to fill the vessel, 2 ton active, and you see a lot of course, you see field shaping, copper structure to shape the field to keep it uniform. You see a lot of white stuff, which is Teflon, which we use as a reflector, but also as an insulator in these materials, in these, experiments. And the volume is seen by 248 or so PMT the top and bottom array, and the distribution of this photon multiplier in the arrays, of course, is done carefully to optimize light collection and also position sensitivity. And this is the typical Wimp signal. I mean, this is a signal from Xenon 1 ton. Just to give you an idea, what are we facing here, where you're talking about few photoelectron S1 or prompt light signal, and even after amplification in the gas phase, we have a charge of few hundred photoelectron, or you are actually counting single electrons in a signal like that. So this is what we're looking for. Xenon 1 ton, as I mentioned, was the largest 1 meter drift, which had not been done. From Xenon 100, we go to 30 centimeter drift to 1 meter. Now we're going to 1.5 meter, in case I forget. So we keep challenging ourselves in having these electrons drift in this long distance and 1 meter diameter or so. The power of combining the signal was already mentioned in the EXO and EXO effort. By using the simultaneous detection and combining the two signals, we get a much better energy measurement. And in fact, this is the results from Xenon 1 ton, where we show an excellent linearity and resolution from keV to MeV. So with an energy resolution at 130 at the 136 double beta decay energy at 2.5 MeV, which is better than 1%. So this is competing, but it's a nice proof that these two signals are really powerful in measuring the energy of the particle, as has been done in Xenon 1 ton. So these are the TPC which have been developed as far as I know so far. That's where we are going. We have the Xenon family of detector from Xenon 10 is not even shown. Xenon 100 with 62, followed by this Lux, a few hundred kilogram later. Then the Panda X in China with a 500 something kilogram, and then Xenon 1 ton, which leads the field. It's led the field. And then we had also on liquid argon, we had much less development. We had dark side 50 with a 50 kilogram target. And so we have gone, actually what's impressive of this technology on the two-phase TPC, at least maybe it's written here, from 10 minus 43 square centimeters spin independent cross section when I started to 10 to the minus 47 or so. So many, many orders of magnitude in about 10, 15 years' time. That doesn't happen so often, especially not in astronomy as well. But impressive progress with this two-phase TPC. And the reason why it has been impressive is that we have not only been able to scale up this detector, because scalability is one of the most important feature that has attracted attention, but we have been able to reduce at the same time the background in this detector, or we wouldn't have won anything. So you can see the size of this active mass in these experiments up to Xenon 1 ton, but you see also the Xenon 10 kind of background. This is events per ton per keV per day when we started, and so Xenon 1 ton has been able to show the lowest background, 0.2 event per ton per kilogram per day, which is impressive. And we are aiming at reducing this background by another factor of 10, which I don't know how I can even say, but the goal of Xenon N ton is to further reduce this background by an order of magnitude. So scalability, and at the same time reducing the electronic recoil background, which the holy grail is going to be for us, this electronic recoil background dominated by intrinsic radioactivity in these liquids, and especially the radon 220, which seems to be a common denominator for all the experiments because it's always there. So this is going to be our fight. Of course, the lowest background that I've shown you for Xenon 1 ton, and as Christian showed yesterday already, has enabled us to do a lot of searches other than the standard Wimp search. I guess I need to move, including these beautiful results on the 2 neutrino electron capture in Xenon 124. That was thanks to the low background and good resolution of this detector, despite being so big. So the next step is this generation 2. I'm going to run out of time. This is a list of challenges. I mentioned already some of them. The main one is to reduce the krypton. I'm sorry, the krypton, we know how to do it. We need to reduce the radon to 1 to 2 microbecquerel per kilogram in all these detectors. And we were at the level of 4 or 5 microbecquerel per kilogram in xenon after some improvement in xenon 1 ton. So, of course, we have to shield this experiment. We are getting to a sensitivity level which is so pushed that we need really to, and also we are increasing the size, so electron lifetime or the ability to keep this thing clean is important. Xenon 1 ton, I'm glad you showed this nice picture. So going from xenon 1 ton to n ton, if you come to Gran Sasso, that's where 1 ton is or was, you can see this structure. We are reusing for xenon n ton most of the system that we built for 1 ton, and so all the system that we have made operative. What we are building new is a new detector with 8.4 ton, 6 ton or so active xenon. We have built a new liquid xenon purification system to be able to pass this xenon in liquid phase through appropriate filters to achieve very long lifetime very fast. We are building a new cryogenic distillation for radon to remove this 222, and then we are building a neutron veto in the same water tank that we have used as mu and Cherenkov. So these are the 4 items. I just give you, of course, the goal is to go, as I told you, another order of magnitude in sensitivity with 20 ton year projection with respect to 1 ton. So here's just a flavor we are putting together. As we speak today, we get emails from Gran Sasso that the TPC is being assembled. These are some of the components. I told you already we are doubling about the PMT. It's 1.5 meter by 1.3 meter diameter. We should start filling the 8.4 ton of liquid xenon in the next month or 2. So that's a major enterprise, but the TPC is being built. This is the size of the vessel, and this is Elena to show you. I look smaller and smaller next to these vessels, but this is the pot in which this guy fits. We have spent a lot of last year in perfecting this liquid purification system to purify this liquid in liquid phase, but the bottom line is that, since I'm running out of time, using liquid pumps and different filters, a very complicated system, but the bottom line in our commissioning tests, which have almost completed, is that we can get the purity of millisecond, if you like, in a few weeks with this new liquid purification system. If we would have purified the xenon as we did in xenon 1 ton or other people in gas phase, we would need 80 days, months to purify. So that's been a major, major accomplishment. Another major accomplishment is going to be the radon column that the group of Christian here, Weinheimer, is building. And to make him happy, since I don't have time, but I have the movie, come with the movie. These are the beautiful pump that Christian group has put together, these magnetically coupled pumps to enable this the radon column to work. And this is the collaboration, 180-something people from 27 institutions. We get more and more, but younger, except me. But so we have a competitor, of course, we are not alone. There is another experiment of similar scale, even larger, the Lux Zeppelin Experiment at SURF. In 2020, they also want to start, so we are going hand in hand, and we see who is going to start earlier. This is another liquid xenon two-phase TPC with a different type of shielding, but essentially is the same principle. And the goal is to have, with 7 ton active, so a bit larger than xenon n ton, and they claim 5.6 ton fiducial. So LZ is going very fast in assembling. There's a lot of pictures we hear from each other, so they're assembling the detector and the infrastructure. They had to start from scratch in terms of infrastructure, because from Lux to LZ is a big scale, from a few hundred kilogram to 10 ton. Whereas we are reusing a lot of the infrastructure we built for the 1 ton. So in the US, we have LZ, but now we all realize this is a very healthy competition, because we have 2 experiments starting almost at the same time with liquid xenon. And so we need, of course, another target, because complementarity of target is essential. We have dark side 20K at Gran Sasso, as it was mentioned by Luciano yesterday and others maybe. So this is another noble liquid. Is a 2-phase TPC with 50 ton of depleted argon, where the depleted argon has been proven already. This is a big structure at Gran Sasso. where you have this acrylic vessel, thanks to the legacy of the Deep 3600. There's a strong Canadian component in dark side. It will be an acrylic vessel surrounded by a 600 ton of atmospheric argon as a veto, other than in addition to some gadolinium-loaded acrylic surrounding as neutron veto. They have two separate cryogenic systems for the depleted argon, which you can imagine is very costly and very lengthy to get, and the atmospheric argon. And of course, the innovation of dark side, since the phototube for liquid argon, much colder, didn't work as well as the ones in liquid xenon, they have put a lot of effort in developing silicon PM, which work in liquid argon. A lot of progress has been made, and there will be about 8,000 silicon PM in this detector, both in the inner detector and in the veto. A big effort, a big structure. It will take half of the old SIA Grand SAS, so this is our rendering of this dark side 20. It should start in 2022. Let's hope. It's very challenging, actually it's interesting to see this plot if it's correct. I haven't done it, but it's true that the sensitivity reach of a liquid argon detector is going to be actually, which is shown here in red, is going to be even more promising at high mass with respect to even LZ or Nton, because of the nucleus of argon and because of the discrimination. So because of the background-free, let's say, assumption. So they have made a lot of progress in showing this discrimination. I took these slides, in principle, what has been shown is that the 10 to the 9 background rejection of electron recoil based on PSD in deep 3600 or 10 to the 7 background rejection is key to keep these hundreds of ton-year experiment to be background-free. That's is a key issue. The depleted argon has been demonstrated, and you can see here an example in dark side 50, where they had a reduction of 1 to 1400 here. Impressive, and of course for dark side 20K, you need 50, 60 ton of this stuff. So it's going to be produced in Colorado with Urania facility and then cleaned in Sardinia. It's a big, big enterprise. Promising, probably will start a few years later than this, for sure a few years later than LZ and Nton. And of course, what I wanted to bring is that it becomes essential to have some other target than xenon. So because if we have both xenon and argon, we can actually constrain the mass of the Wimp and the cross-section a lot better. So I stop here because I ran out of time, and just to say that the scalability and low background demonstrated by these noble liquid targets make them the most promising way today to search for Wimps, and hopefully in this decade we will nail down the Wimp idea, put it to, or we'll find them. Thank you.